Hello everyone, this is Jie and Chen. Our project is Wafer map failure pattern classification using deep learning. We choose this topic mainly because both team members are from a wafer inspection company. Wafer inspection is very important for improving the yield in a semiconductor fab. Based on the wafer failure pattern, it is possible to figure out the root process cause. The data we used is the open source data on Kaggle. There are a total of 25,000 wafer data with 8 different classes. One issue for this data set is that the dimension of the wafer map image are not the same, which prevents deep learning to be used. Therefore, we resized all the wafer map to the same dimension. We calculated the weighted average dimension as 42 by 42 pixels. The other issue for this data set is that its distribution is highly imbalanced, so we applied image flipping and rotation for data augmentation. As for the training and testing data splitting, two different approaches was used. Approach 1 is first augmentation and then splitting. Approach 2 is first splitting and then apply the data augmentation only on the training set. Compared to approach 1, approach 2 excluded the augmented data from testing. This may produce more accurate evaluation for the model. Two different networks was explored. First one is simplified AlexNet. The second one is simplified VGG16. The simplification does not mean to reduce the number of layers, but reducing the number of filters on each layer. Because our images are much smaller and much simpler, in addition, our goal is to classify only 8 defect patterns, while AlexNet and VGG are targeting much more than 8. Then let's take a look at the results. In the AlexNet, approach 1 and approach 2 produce very similar performance. Without any regularization, there is a high training accuracy but relatively low testing accuracy. With the help of L2 regularization and dropout, the variance gets reduced at the cost of higher BIOS. Such trend demonstrates the ability of L2 regularization and dropout on overfitting reduction. In the case of VGG16, for approach 1 without dropout, the network shows almost perfect accuracy for the training set and 92% accuracy on the testing set. This proves that a deep network can reduce the BIOS. However, in the case of VGG16, approach 2 does not converge to a global minimal. To see how the model performed on each specific class, confusion matrix is generated. We also performed hyperparameter tuning on the learning rate, L2 regularization coefficients, and the dropout rate. It turned out that lambda is the most sensitive parameter to our model. To summarize, in this work, we implement a simplified AlexNet and VGG16 network for wafer pattern classification, and both networks beat the machine learning benchmark on Kaggle. Finally, thanks for your attention. Please email us for any questions.